Hello, WebRTC Pong is a toy I created to learn about peer-to-peer rollback netcode and about WebRTC. The focus was never really about Pong, but if you just want to play Pong, then head to mitzella.com/Pong, click Host Game, get a friend to click Join, and it should form a peer-to-peer connection with rollback netcode. If it doesn't manage to connect, it might be to do with the type of internet connection you have. If both people are using CGNAT, then it probably won't work, but I've had reasonable success playing against a few different people. The rest of this video is going to be about how it works. As we all know, the internet is a series of tubes held together with duct tape. And one of the biggest balls of duct tape is NAT, or Network Address Translation, using NAT to compensate for the fact that we've run out of IPv4 addresses. The way it works is you have your home network, and this will have your computer, maybe your phone, connected to Wi-Fi, and maybe some other devices as well. And over here we'll have the internet, and in between them we've got NAT. Now when you make a request, say you want to visit a web page, the packet will go out through the NAT, and this will translate that packet. That is, it will change the source IP and port, and then send it off through the internet until it gets to the web server. And the web server will respond to where it thinks that packet came from. It may or may not take the same route back to here, and when it gets to here, the NAT will identify that packet, look at it, and remember that this outgoing packet was the request, and so it knows that this response needs to follow the same route back to that computer. Now this is all well and good if you just want to look at a web page, but if you want to host something on this network, say a video game or a video call, then you've got a problem, because if a packet comes in out of the blue, the NAT doesn't know what to do with it and throws it away. Now, you can configure your NAT to dump all unknown traffic onto one device, or you can set up port forwarding, where you say anything that comes in on this specific port should always be mapped to this computer. And traditionally that was the way of solving the problem. The problem is you can't really expect Joe Public to be fiddling around with port forwarding and NAT configuration when all they want to do is make a video call. So we needed something automatic. There is something called UPnP, which is supposed to be a way of automatically configuring network hardware. And you can, if your NAT supports UPnP, then you can technically use that to tell it to set up particular port forwarding. And while this does work, UPnP is just disgusting and unreliable, and I hate it. So let's pretend it doesn't exist. And also, because of the invention of hole punching, UPnP doesn't need to exist. Stun stands for Session Traversal under NAT, and stun lets us do UDP hole punching. Now the stun protocol is very simple. It's just a single packet, only a few bytes. You make a request to the stun server, and it will respond saying your outgoing socket looked like this. That is, your outbound IP and port number were such and such. And we forward that information to the person we're trying to video call, and we tell them to connect directly to this socket. And most NATs are so stupid that when they receive anything on that socket, they'll assume it's from the stun server and forward it back along here to the computer we're trying to talk to. And that's it. We now have a peer-to-peer connection through NAT. Now, some types of NAT will be a bit more particular about this. They'll say, hang on, this packet source IP doesn't match the stun server's IP, and give you a bit more fuss. But in the vast majority of cases, UDP hole punching just works. You can even go deeper with this. You can it's possible to hole punch a TCP connection, which is kind of crazy, but all you have to take away from this is WebRTC lets us perform stun in browser. Now that we have a data connection between browsers, it's time to think about netcode. The simplest and worst way of making an online game is to have one player host the game, and the other player just sends their inputs and receives back data about what to display. But that's terrible, because this player will have a distinct disadvantage, because everything they do and everything they see will be delayed by the time it takes packets to travel back and forth. To make the game fair, we need to make sure that both players see the same thing at the same time. At any given moment, their monitors should be displaying the exact same image. We also need to make sure that they have the same input lag, that is, the time it takes between pressing a button and it having an effect on screen needs to be the same for both players. Another goal to aim for is to have a consistent frame rate. The network connection is going to jitter somewhat, and if the game slows down every time this happens, it can be very jarring, particularly in fighting games where combos depend on accurate timing. If the game is speeding up and slowing down, it can be very frustrating. When we talk about frame rate, let's first be clear about what a frame is. The computer monitor will have a fixed frame rate. That's unlikely to be the same frame rate at the other end, but even if it is, they're unlikely to be in sync. So for now, let's consider a frame to simply be an event, a point in time where we process our game logic. Every time a frame happens, we listen to the player's input, we recalculate the state of the game, and then wait for the next frame. At 60 Hz, that will be about 16 or 17 milliseconds. The other thing to be clear on is we want to make our game completely deterministic. So for a given set of inputs, the game is completely predictable. If the player pressed this on frame 1 and that on frame 2, it'll always result in the same thing happening. This doesn't mean we can't have random elements in the game. It just means that we use a pseudo-random number generator and synchronize the random seed at the beginning of the game. So because the game is completely deterministic, we don't need to share any info about the state of the game, no matter how complex the game is. The only thing we need to send across the network is the player's input. Let's look at how delay-based netcode works. Let's have two timelines, and call the players Alice and Bob. We start by measuring the ping time, so we just send a packet and respond to it as fast as possible. And we might do this a few times just to average it, but basically let's assume that we get this response 50 milliseconds later. And from there we can infer that the time it takes to go halfway, or one journey, is 25 milliseconds. That is assuming that the route is symmetrical, which it might not be, but if it isn't, we have no way of knowing, and in practice it's generally a safe bet to assume it's mostly symmetrical. To start the game, the host sends a message saying, "Start the game now," and then waits for 25 milliseconds here to begin frame 1. And hopefully that packet will arrive roughly the same time, and the other player will begin frame 1. And then both players will do each subsequent frame 16 milliseconds later. Since the game's deterministic, we can only process a frame when we have both players' inputs. So at this point in time, all we have is our own input, which we can measure and store in a buffer and send to the other player. So if it's 25 milliseconds, it will get there somewhere between frame 2 and 3. And the other player will do the same thing. They'll send their input to us. And there's nothing else to do at frame 1, so we go on to frame 2. And here, once again, we can measure our input, store it in a buffer, and send it to the other side. And Bob will do the same thing. Now at frame 3, we know what the other player's input was for frame 1, and we know what our input was for frame 1, so we can start processing the game logic. So the logic for frame 3 will use the inputs from frame 1, and similarly, the logic for frame 4 will use the inputs from frame 2, and so on. Both players should see the same thing, and should have the same amount of input lag. But there's a few problems here. First of all, even if this initial ping synchronization was perfect, After a while, these frames will start to drift out of sync, and then one player will start to see things before the other. Secondly, what happens when there's network lag? We can make our buffer bigger so that there's more input lag, but if the buffer ever does run dry, the only thing we can do is wait for more data to arrive. So in that case, these frames will definitely go out of sync. Getting things synchronized is a lot like the way NTP works. Both Alice and Bob will have a local clock, which won't be in sync, but they will both tick at the same rate. If we take two packets and we measure the time they're sent and received, this will be T1, measured by Alice, T2, measured by Bob, T3, Bob, and T4, Alice. Now, even though Alice and Bob's local clocks might be wildly different, the difference between T3 and T2 will just be a number in milliseconds, and the difference between T4 and T1 will also just be a number in milliseconds, and the difference between those differences will give us the ping time. And this will work for any two packets. So long as we append the relevant timestamps to every packet we send, we can form a running estimate of the ping time, all the time. When we send our input to the other player, we can also send an estimate. We can say, I plan to draw frame 3 in so many milliseconds. And when it gets there, we can look back. We can say, oh, well, I drew frame 3 so many milliseconds ago, and we know what the ping time was, so we now know everything we need to calculate what the lag or lead time is between frames at each end. And once we know that, it's a simple matter of constructing a control loop to compensate for it, which just means fiddling with numbers until we get it critically damped. Finally, we can be sure that both players see the same thing and have the same input delay. There's one last thing to worry about before this delay-based netcode can be considered complete. That is how these game frames relate to the drawing frames. The display's refresh rate is completely out of our control, and while the game might run at 60 Hz, some monitors refresh at 59.94 Hz or 59.7, or even if it's exactly 60 Hz, the game might not run at 60 Hz due to network lag. And whenever you have two frequencies that are almost but not quite the same, then you get a beat frequency. And this will manifest as a game stutter every now and then. If you imagine we measure the time between the game frame and the next drawing frame and plot it on a graph, it might look something like this. And the timescale here would be something like 30 seconds. Our frame sync number would start about here and then creep upwards. And when it gets to 16.7 milliseconds, it will drop right down and continue onwards, form a kind of sawtooth. Except things are never as clean as this, and whenever the value is near this transition point, it starts to get messy. Within some tolerance, which I'll call the danger zone, we're essentially asking for the game frame to happen at the same time as the animation frame. So we're at the mercy of the browser and the OS as to which one gets processed first. So what we actually see is something like this. In this region and this region, it's nicely alternating game frame, drawing frame, game frame, drawing frame. But here it might do 2 game frames, then 2 drawing frames, then whatever. Even though our netcode is working perfectly, visually to the player in this region, it will drop to half the frame rate. Some people might not notice, but I find it annoying. But now we know what's going on, solving the problem isn't too difficult. We simply detect when the frame sync number is approaching the danger zone and enable a delay, which I call sync tick, to get us back into the stable region. And once we're clear of it, we turn off the delay and continue as before. This delay will be much less than 1 frame, so its effect on the game logic will be negligible. But the benefit is that we'll only get 1 dropped frame every 30 seconds or so. Okay, at last we have working delay-based netcode. Here's footage from an early prototype, and my phone is on 4G here with a ping of about 50 milliseconds, yet as I move the paddle we can clearly see that the phone and desktop displayed the same thing at the same time. You could play it looking at either screen. Now that we've got it working, let's talk about why delay-based netcode is not good enough. A game like Super Smash Bros. Is very sensitive to lag. And you might argue that so long as the lag is symmetrical, then the game is still fair, but it's not as simple as that. Even if both players see the same thing, and input lag is the same for both, and even if the frame rate is consistent, it still might not be fair, because the game is made up of a mix of characters that are carefully balanced. For instance, some, but not all, characters have projectile weapons, and these have all been nerfed in some way. Either they take a long time to charge up, or the projectile moves slowly enough that the opponent can react. They can dodge or block if they see it coming. But if the input lag becomes big enough, then by the time you see on screen the weapon being fired, it's already too late to react. That's an extreme example, but the balance between characters does definitely change when the lag gets bad. When I tried to play properly with the sword fighting characters, I found it really hard to win matches. But when I went as Bowser and just stomped on everyone, I made it to so-called elite ranking in a single session, simply by virtue of being obnoxious. I'm pretty sure my Bowser tactics would not have worked in a local match. It's all very disappointing. And the sad thing is, it didn't have to be this way, because there is an alternative to delay-based netcode. Let's talk about rollback. Picking up where we left off, let's say some packets are delayed, and when we reach this frame, we don't know what the other player's inputs were. But instead of just waiting, this time we'll do something different. The first thing we do is we save the current state of the game. We take the player positions, the details of every object, the scores, even the current seed for the random number generator. We take all of this info and we turn it into a blob, which we put to one side for safekeeping. Next, we make up some inputs, some random inputs, and just pretend that's what the other player told us. Usually we just repeat whatever their last inputs were, since statistically that's a reasonably good guess, but it doesn't actually matter, it doesn't need to be an accurate prediction. And then we note down our inputs, send them to the other player, and proceed to the next frame as if nothing happened. At this frame, let's say we still haven't received any more packets, so we still don't know what the other player's inputs were. So, as before, we just write down what our inputs were, send them to the other player, make a guess for what their inputs were, and carry on regardless. When we finally do get some packets containing the now historical data for what the opponent did, we very quickly correct for it. We load this save state, overwriting everything, and then quickly replay the game using the inputs that we now know for both players. If we have enough data to return the game to the present, then great, but if not, all we do is save state as far as we got, overwriting this one as the new true state of the game, and then run our predictions forward again into real time. That's it. That's rollback netcode. And the effect is that the game plays exactly as if all the inputs had arrived instantly. There's almost no input lag, and if the network lags, the game continues to run at full speed, with just the opponent's character occasionally stuttering as it corrects the predictions. In the case of our Pong game, our paddle is always smooth and always responsive. And to the opponent, their paddle is always smooth and responsive. And to both players, the ball's motion is totally smooth and in sync. Conceptually, this kind of rollback netcode is really not that complicated, but there is a much higher CPU load associated with repeatedly recalculating the game state, so perhaps we can forgive Smash Ultimate for not managing it. Except there is a fan-made ROM hack/emulator hack that implements rollback netcode for Smash Bros. Melee, called Project Slippy. And this is a phenomenal achievement. There was a serious amount of reverse engineering needed to get this to work. I haven't actually tried it yet, because it's years since I've played Melee, and I expect I'll get slaughtered immediately. But I just love the idea that what Nintendo, with their $1 million budget, didn't manage, a group of dedicated fans did. To conclude, making this was pretty fun. I've simplified a few bits of the explanation, so if you want more detail, check out the project page on my website. mitzella.com/pong is the game demo. mitzella.com/WebRTC Pong will take you to the project page. I should also say, most of what I've talked about is original research or my own musings, and might be entirely wrong. Don't take anything I say as gospel.